Sometimes in all the talk about sucking and squeezing and banging, we forget about the blowing part. Blowing is important too.
My name is Richard Waitas. I'm the Senior Manager and Spokesperson at Magnaflow Performance Exhaust. I started out at Magnaflow as really an entry-level person. They weren't hiring and didn't actually need an engineer, and that was kind of my background. So I ended up starting off as a dyno tech, and from there kind of grew the position into working my way through building and fabrication, from fabrication getting into design, from design to running the floor as a foreman, and eventually as the engineering director. From engineering, I kind of moved into some of the sales and marketing positions. Having the background in how our product worked and developing those pieces gave me the background to tell our customers and consumers exactly what our products did and how they worked. Well, an exhaust system really only has one primary function, and that's to evacuate exhaust from the cylinder head post-combustion and getting it away from the car. Understanding the design of an exhaust system and how it appears in most stock vehicles, and of course how it will change as it becomes a race or optimized aftermarket application, has to do with understanding what the exhaust does. And what you're looking at is how to get those exhaust gases out from the cylinder head and pass through to get to the end portion, whichever is going to be your tailpipe for the purpose of evacuation, but doing so in the most efficient means possible. So one of the first interaction points of an exhaust is actually what happens post-combustion. So we're talking about what's happening inside the cylinder when you've reached ignition, and finally when that cylinder is pushing up in its last stroke, the exhaust stroke, and moving out that exhaust valve. We've got a lot of turbulent air coming out, swirling outside. It's high temperature, and it's leaving that exhaust port at very high gas velocity. Understanding what happens to those gases as they traverse through the different shapes and sizes of collectors, headers, cast manifolds is really what the science behind developing an exhaust system is based on. Our first interaction in developing an exhaust system is at the cylinder head. Obviously, we're given parameters set by the OE that give us a certain exhaust exit velocity and a certain amount of CFM. When we design that header or manifold, we want to make sure that we're not creating a restriction by allowing for too little exhaust gas exit, and we don't want to create a disturbance of laminar flow either. Oftentimes, we want to create an immediate turn as it comes outside of the cylinder head, but what we found through testing is that if we can create a straight exit off the cylinder port and then create a more gentle bend, you'll get better exhaust flow through the entire exhaust system. That first bend is usually a function of fitment. You take a dragster, for example, with those long zoomies out the side. They have very small port angles and a very long straight tube that comes out, and the car is actually physically designed around optimal exhaust. Now, in most cars that we're working with, we've got a car that's got packaging where the exhaust can't simply exit the engine compartment right where the port is. So now we're introducing our first restriction, which will be that first bend. Once we've got that intact and we kind of know the direction we're going with the exhaust, we need to know what diameter we're working with, and of course, how and what direction we're going with the exhaust system as far as whether we're going to a 4-into-1 type collector or a 4-2-to-1, and these will help determine the packaging to get the exhaust out the way we need to. One of the most critical things on design for the exhaust system is picking out your primary tube diameter. Now, this is a function of simple, how many CFM do we have coming out of the motor at peak exhaust valve lift? Once we know that CFM, we can appropriately pick the right size diameter. If we go too large and it's not going to promote good flow from the port, we can actually create a restriction right there at the port. If we go too small, same problem. We can actually neck it down, and now we're going to create another pressure outside the port, creating more restriction for that exhaust exiting that cylinder head. So let's say our port exit point has a diameter of X, and we want to go X plus maybe 1/8 of an inch. If we take that 1/8 of an inch larger volume, what we're doing though is we're creating a small expansion point. And as we know, as that exhaust gas comes out and starts to expand, we're slowing it down. So now that gas is traveling at a lower speed as it travels through the rest of the exhaust system, which means as it passes through all the rest of those components, it's going to continue slowing down. Picking that proper tubing size so that transition is almost seamless will cause an effect that keeps the exhaust gas velocity high and delivers the exhaust out with the most efficiency out the tailpipe. After determining the proper tube diameter, we want to know how long does that tube have to be. And there's a bit of a science that goes behind it, and that's really understanding the first interaction of where we're going to create our first scavenging effect, which is where the collector sits. Ultimately, it's about understanding how that exhaust pulse exits the cylinder head, travels through the valve, outer port, down the tube, and gets to that collector. The moment that it expands from that small diameter tube into that large cavity, which is the collector, we create a negative pressure wave, otherwise known as a vacuum pulse. And this is traveling back to the cylinder and will help evacuate some of those gases that have already been spent by combustion. What we have to understand is to create proper scavenging, we need to know when that cylinder is moving up from bottom to dead center, starting to push that exhaust pulse out of that valve, and when that valve starts to open. So that exhaust valve open event becomes our minute restart timing. And what we've got to look at now is you've got an exhaust pulse leaving at 80, 90, 100 plus PSI out of that cylinder head, and we have a pressure wave leaving, and that pressure wave is traveling at the speed of sound. So we're talking about something traveling at 1,100 feet per second. So we've got to do a calculation and understand that that exhaust pulse, as it's leaving, is now traveling down a tube. And at 1,100 feet per second, how many seconds of crank rotation does it take for it to get down to that collector, and then how many seconds to get back? And what we want that distance and time to be is before that exhaust valve starts to close. Because once that exhaust valve is closed, we're no longer getting the benefit of creating that vacuum to help evacuate the cylinder. We want to make sure that we get that exhaust pulse back from the collector in time to make sure that we can help evacuate any of those burnt gases. When the OEMs are building manifolds, their first primary constraint is really not optimal performance. And as we get into higher performance cars, they do tend to lean in and design more that way. But primary is going to be getting that exhaust gas pulse directed the right direction and underneath the car into an exhaust system that's designed around fitment and noise suppression, not necessarily optimal performance. But now we're talking about how do we get into something that can actually start helping the exhaust evacuate the system. That's when we look into 4-1 style collectors, or even now the 4-2-1 tri-Y type designs. One of the first designs we had talked about as a way to collect those gases and create that first collector point is a 4-1 style collector. This is probably the most traditional one you've seen. Oftentimes in the long tube forms have been called bundle of snakes and things like that. And mainly why? Because packaging. Why is it so intricately twisted? Well, you want to make sure that the tube lengths are near similar size, but then you also have to get around all kinds of things on the car, whether that's frame rails, whether that's transmission, and other components. We find that we have to do a lot of twisting and turning. This does sometimes become a drawback when you're trying to use very large tube diameters in race applications where you're using 2-inch primaries. If you can imagine you have 4 2-inch primaries going into a collector, your cross section on that, you're looking at something where those tubes are touching of over 4 inches. And that is something you got to put somewhere underneath a car that usually is lowered for high performance reasons or doesn't have packaging for tubing much bigger than a factory, maybe 2.5-inch exhaust. So that system in itself proposes some difficulties. But the benefits that you get with a 4-1 style collector is you get a very large peak torque boost. As that exhaust pressure wave comes down, and if you've appropriately timed it to the correct length, you get a very strong negative pressure wave, because as that exhaust pulse leaves that small diameter tube and has a very large cavity to expand on, you get a very strong negative pulse, otherwise known as a vacuum, sucking down that tube. If you have a smaller collector with a smaller tube, of course, that event becomes less impactful as the expansion is less as well. That also brings us to our next style, which is like a 4-2-1, oftentimes called a tri-Y style header. The tri-Y headers now work a little differently. Instead of having all 4 tubes going to one single large collector event, which creates that pressure wave, we're going to create intermediate points. So we're going to find paired cylinders, and these are cylinders that on the same bank would benefit from the cross pulse or the negative pressure wave from that cylinder, and we're going to pair 2 of those closer to the cylinder head. That'll create a smaller pressure wave difference. As we have a smaller collector, we might have primary size that goes from a 1 5/8 to maybe a 1 3/4. And that 1 3/4 pipe may even be a 2-inch pipe as the 2 collect together. But as that small increase happens, we're creating a small pulse behind it. Now, it's not as strong as what we've seen with the 4-1, but now we're getting our first pulse maybe halfway through that exhaust stroke and helping pull some of those gases out before we reach the top of that valve event. Then we have our second collector point, which happens and pairs those other two sides, and we get another pressure wave. Again, not as large of an event as far as expansion because the collectors are smaller, but now we've created 2 points where we're slowly drawing more and more of that exhaust gas out. And what we find is we get an average increase of torque and horsepower over a broader range rather than a single peak that you get with the 4-into-1. There really isn't one that's best suited for all. If let's say you're building a drag car and acceleration and straight line is everything you're looking for, you'll find that 4-to-1 and that massive torque boost you get is great for just that car, where you want a big amount of torque and you got a loose torque converter and you're really worried about getting acceleration overall as being your peak output. But then if you take a vehicle where average power is more important, let's say a road race vehicle, an off-road trophy truck where you're traversing the entire power band up and down all the time, that average torque might actually be more beneficial. Where the torque starts to fall off in the 4-to-1 style, the 4-2-to-1 will continue to pull. And that average torque will net you a car that has better average acceleration and overall best track speed. So when you're talking about something where you're not trying to get from point A to point B in a straight line the fastest way possible, but making it around corners where you have transitional speed, you'll find a 4-2-1 style will give you the most average power increases overall. So that gives you an understanding of what pressure wave tuning is. And really, one of those keywords we see oftentimes in marketing is scavenging. And scavenging is just another word for pressure wave tuning. It's understanding how that negative pressure wave interacts with the cylinder to create more evacuation, meaning more good air in, more horsepower out. Now that you've seen what the benefits of the 2 different style collectors are, usually we run into our next exhaust component, which can be a catalytic converter. Now we'll talk a little bit more about catalytic converters and how they interact with today's emissions-controlled vehicles. But in the theory of exhaust, we're going to go ahead and omit that now and talk about our next point of interaction, which can be our crossover. We're going to continue that same concept of scavenging, and we're going to take it to that next level. So the X-pipe, as a lot of people have heard of it, came about in NASCAR. You know, everybody was talking about what they had to do to create the best X-pipes in NASCAR and why they were used in NASCAR, and really what the function is. Now, there is an acoustic function for crossovers that provides a sound that people like and for tuning. However, that sound is created by the combination of exhaust pulses, and that's exactly where we get the same type of interaction we had with the primary tube and the collector, but now we have 2 pipes coming down from both collectors into another interaction point, and we can create another point of scavenging. Again, the whole idea behind this is to help pull more of those exhaust gases through the exhaust system using the waste energy from the other side, in this case, or the other bank of cylinders, to help move that exhaust at the highest speed out the back of the vehicle. What the header and collector design established, now we need to determine what the tube primary design is for the rest of the exhaust. And like the primary on the header, we need to determine it based upon the CFM airflow of the entire bank of tubes that are coming down to that collector. With the primary and collector design established, the next system that we have to look at is going to be the exhaust system primary diameter. Now, in a dual exhaust, this means we have 2 tubes, so we need to take the total output of the motor and look at how much CFM it's pushing and divide that by 2. We have a typical formula that we'd like to use, which involves understanding some of the volumetric efficiencies of the motor, some of the parasitics, and what happens with internal combustion. But through a lot of empirical testing, we've also found that 2 to 2.1 CFM per horsepower nets us an exhaust system with minimal exhaust resistance. So as an example of how we actually calculate that tube diameter, let's use an example of a 500 horsepower vehicle. So if that car is making 500 horsepower at the motor, we're looking at about 1,000 CFM of airflow. And with 1,000 CFM of airflow, we can choose between a single exhaust, which we would need 1,000 CFM of support, or a dual exhaust, where we would need 500 per bank. So in this particular example, we've been working with a V8 model, and we've got 2 sets of headers, so we're going to stick to that dual bank kind of theory. Now, with 500 CFM of airflow required, we want to select a diameter of tube that can support that. And this will take some bench work, and in this case here, this is where we introduce our flow bench, and we can go through and flow the different diameters of tubes to determine how much CFM each tube will support. And in our testing, we have found that 500 is kind of one of those transitional points where we would go from a dual 2.5 to looking at a dual 3-inch to get the appropriate amount of support for the horsepower at peak. Today's vehicles are much more engineered, and people understand that because, I mean, I remember growing up and the 396s and the 454s, the big block Chevrolets, those were the monsters and kings, and they were making 400 horsepower. Today we've got 4-cylinder, 5-cylinder, even some of the six-cylinder stuff that's with the aid of a turbocharger, making that power on a car that's making 30 plus miles to the gallon. So times have definitely changed, and I think a lot of those old adages of what makes a vehicle a high-performance vehicle, and understanding that bigger isn't better, because I mean by that means some of these cars from factory that are making, let's use the Charger Hellcat or the Challenger Hellcat at 700 horsepower. If we took that basic equation of what we thought old exhaust should be, we'd be running 5-inch exhaust tubes out the side of those cars. But you know, that's a factory 2 3/4 inch and a 3-inch exhaust. So times 2, of course, is a dual. But for the most part, the size part is definitely considered by the factory. And I think people understand a little bit more that it's not just about open. It's not about just getting it out. With the header design picked, the collector, the tube diameter selected, and a crossover, the next device we're going to run into in the exhaust system is the muffler. And now the muffler's really only purpose is to lower sound amplitude. And in some cases, we're talking about creating a sound character for a more pleasant sound. Other cases, it's about having less harsh environments inside the car, whether a race car or a daily driver. We want to make sure the environment inside is only as invasive as it needs to be. And of course, race levels versus street levels are completely different. And really, to get into muffler selection, you need to understand a few different types of mufflers and the technologies behind them. When talking about mufflers, you have a couple things you're looking at. You have active and you have passive. As the name implies, a passive muffler is what you would find in most cars today. This is a device that uses the energy created by the exhaust passing through in the combustion process to actually reduce the total output. An active device is actually much similar to what you would find in a, let's say, a noise cancellation headset, whether you're talking about a headset used for radio and playback or even ear protection when you're firing a firearm. It's taking the world through a microphone, sampling out the environment, and then it's creating a cancellation wave, something at the opposite sine wave to reduce the total amplitude. But that actually requires a measuring device such as a microphone, a listening device. It requires power to generate another pressure wave, so somewhat of like a speaker is required to actually do that. And while those technologies are used, they are not things that you would find in the common market. So we're really going to focus on what's on passive, and in passive there's a couple things you're looking at. We have absorption, and reflection. The two different types of mufflers are representative of what you'll find most of in the aftermarket. A reflection muffler is something that you'll see that has and uses the rechanneling and repurposing of the energy as it's passing through the muffler to cancel out other sound waves by basically bouncing them off of walls and chambers. When you're looking at a reflection muffler, you're looking at a device that has an inlet and an outlet. And as this exhaust passes through, there has to be something on the inside, whether it's chambers, reflective devices that cause the gases to bounce around and travel before they get out. Now, a reflection type device is using the energy, which is the exhaust gas pulse, to reflect that sound wave against each other, hoping that the sine waves will change so that they can actually interact and reduce total amplitude. That'll give you a lower sound. The use of chambers with tuned ports will cause the gases to pass inside, and as they come in, reflect and come back out, you can actually change the sound. So you can now adjust the character. But all of this is done while doing one thing, and that's consuming that energy. And in doing so, what you will find is that the pressure that's created inside by reducing the exhaust gas velocity will decrease your total output. So this now becomes a calculated resistance. So as we have a certain amount of exhaust gas velocity entering, the exhaust gas velocity is down as it exits. In an absorption type muffler, you'll have a core which passes through and has material around a packing and then perforation to allow the exhaust gases to exit the pipe, interact with the absorption material, and as any time we're talking about something that's moving, the exhaust gas pulse has energy that's moving through this packing material. And the packing material allows, much like you would find the fiberglass in your walls, why do we put this packing material that's got low density inside that allows vibration to be absorbed? Well, because that vibration is sound energy. And in the same principle that you're looking at the insulation in your wall, it will actually help reduce the amount of sound that passes through. The biggest thing that you'll notice, though, that there's very little change as the exhaust passes through, so long as the chamber that's inside and the pathway in the tube is the same diameter going in and out. So here you have a very minimal drop, if at all, no drop in velocity. So depending upon what you're trying to do with the vehicle, and of course the limitations of the devices that you have, you'll find that maybe you can use a reflective technology muffler as long as the drop in pressure does not impede upon the total CFM airflow. But in most cases, what you're looking for in the muffler is you're trying to maintain that velocity, just like we've done through all the other components, and making sure that we exit that velocity as soon as possible at the most efficient means. In understanding the ORP absorption style muffler, one of the things to note is how come this muffler with absorption packing and perforated holes throughout the entire system, how come this muffler can actually outflow a straight pipe? And there's a couple things, obviously, when you see this, you're like, well, that doesn't make sense. You're slowing down things. And it has to do with understanding the dynamic nature of what an exhaust system does based upon wide open throttle, which is when we want the most horsepower, and cruising speed. Selecting the absorption style muffler, we know that at slow exhaust gas speeds, as it's coming through, we're going to see those gases exchange through the pipe, go through, and we're going to reduce the sound. In dealing with our product line, obviously, in what we deal with at Magnaflow, you'll find that we always talk about how we have a wide open, straight through sound, but we have a good, comfortable cruising tone. That comes from the fact that at low speed, all of these gases are forced to go through the hole, because as we come from this tube to this large chambered muffler with packing material, it actually will expand to the path of least resistance. And each one of these holes, it opens itself up into the open packing material, and those gases come out and exchange and move through the pipe. This creates a lot of sound absorption. But what happens at speed is the interesting component. As we start to increase the velocity that we're coming through the pipe at, and this starts getting higher and higher pressure as the exhaust RPM is, as the engine RPM is going up, we find that the exhaust passes through here once and then stays trapped inside the chamber. It no longer is exchanging. So that primary airflow is no longer going down the outside of the pipe and through. We're finding that the majority of the exhaust gases are passing straight through. This is why the sound gets louder on the muffler. This is also why we can see that this starts to flow closer to this pipe and eventually will outflow it. And that's the part that a lot of people don't understand. When you look at the dynamics of what's happening inside here and here, you'll see as air pressure starts to roll down in here, the longer the tube and frictional resistance, we're going to start seeing the exhaust gases slow down around the outside, and eventually the interference will become bigger and bigger, and we'll start to see that the exhaust starts slowing down, and our net effect is, again, we're slowing down exhaust gases the longer the pipe is. When we're talking about an absorption muffler, we've got these perforation holes, and the holes, when you look at the total system inside, can be as much as 30% of the surface area. If we can reduce the amount of surface area that the actual air is contacting metal and slowing down, we can actually have that air column travel faster than if it was traveling down a straight piece of pipe. So regardless of the type you pick, you want to make sure that not just tubing diameter alone becomes your selection point, but the actual flow rate, so that you know that that 500 CFM can be effectively passed through that muffler and not create another restriction. Understanding how a absorption muffler or reflection muffler and how all those interact with our exhaust system is important. But really, for the most part, let's say we've got the amount of sound suppression to the level we want. What's next? Really, that next step is how do we want to change that sound? And really, there is a whole other science behind creating different tonal character based upon reflection, absorption, use of Helmholtz chambers, and other things, which are really no different than really what you would use to tune a wind instrument of sorts. We're manipulating and controlling air pressure waves and in chambers to create different sounds. So when you're talking about what we deal with as a manufacturer all the time, it's I want to make my car sound something, you know, deeper, raspier. I want my four-cylinder to sound like a V8. I want my turbo car to have more depth to it. How do you achieve those sounds? And well, at the end of the day, our mufflers, whether reflection or absorption, they all rely upon what the source is. And we're going to be able to manipulate that, but the core sound is really why you can say, regardless of the exhaust on a car you might have, that was a Ferrari, or hey, that was a Lambo, hey, that was a Mustang. That character is inherent because of the firing order, the compression ratio, and really the way that the manufacturer designed that motor, and all of those things contribute to a character. And that character can be enhanced, it can be accentuated and reduced, but for the most part, you're still gonna have what that is. And understanding that the sound is a function of what the motor's producing and the characteristics of that motor, there isn't a whole lot we can do to really change that. We can add a little bit here, take a little way there, but at the same time, that car will always have that character. Now, there are a couple ways to kind of change that, and in the world of exhaust, you may have heard of some 180-degree headers. These are really popularized and made apparent to the general public, I think, in the race world with the old GT40s. They actually took a pairing from one of the opposite firing, 180-degree firing cylinders and crossed the left bank to the right bank. In most cases, you have to work with each bank as its own set with the collectors. In this case, the packaging allowed for the exhaust to run down the motor and out the back in the middle, and they paired two cylinders that were firing 180 out and switched them into the appropriate cylinder, so now you had true pulses arriving at the collector exactly spaced at 180 out. This gives you that same effect if you've ever heard of cars that had 180-degree plain cranks. Their firing order is distinct, which creates a different noise. And if you actually change the exhaust arrival in the collector, you can get a car that isn't a flat crank style firing to have one that has a sound that's much more similar. With the majority of the exhaust system already complete, the last part is tailpipe. And a lot of people ask, do you really need a tailpipe? And the answer, of course, is no, you don't need one. But the tailpipe serves a couple of purposes. Obviously, the exhaust system, if you've built an exhaust system that truly is optimized, you're going to find things in places where it's difficult for packaging. You might find a muffler too far forward of a muffler cavity that was provided stock. You may find that the exit points are so far back that you don't have a lot of room for a tailpipe. But the tailpipe does have a net effect on the system. It's just not a major one. It's a big one when you're talking about sound. But again, for performance sake, if you've maintained a tube diameter that's not going to be a restriction, the amount of distance that you put behind it is not super critical. When it comes down to it, if you want a muffler to have more of a muffling effect, you can create a little bit of pressure behind the muffler by a smaller diameter or even a longer tube, and that's going to make that muffler work harder. It will sacrifice a little bit of airflow, but at the same time, if that's open and available for you and you want a sound that's more mellow for the street, you can do that. As you can see, is if you put a muffler that's wide open at the end, much like a collector, you have a atmospheric pressure on the outside and high pressure on the inside. It's going to rapidly expand as it comes out of that muffler. Along with that, though, you're going to get some cold air reversion and a few other things where as that exhaust pulse leaves, it's going to suck in some of that cold air back into it, causes some of that backfiring you might have heard in cars and things of that nature. So it's a part of the design that comes mainly on the acoustic side, but can impede horsepower if not correctly designed and shaped. But at the end of the day, when you're designing an exhaust system, it's really about knowing your application and use. An exhaust system, like most other aspects of your car, are tuned for a pretty narrow window. The difference is being a hard part type modification, you don't have the flexibility of having a wide range of operation. You cannot calibrate an exhaust to work for great low-end torque and high RPM horsepower. You're going to have to pick a range of operation and optimize based upon that RPM and the CFM airflow and what's going on as far as exhaust gas escape velocity at those particular areas. So I oftentimes run into the question of, if I'm buying something on a shelf and this is a part designed for my car, is it really the right part? And the question goes back to making sure that you communicate with the people that designed it and making sure that the part was designed for what you want. The worst thing you can do in the world of modification is buy a part that wasn't designed for your application simply because it fits. And while a lot of times we find ourselves in the exhaust world trying to get from point A to point B is merely the only goal, as we're transplanting a LS motor into a non-LS based car chassis, or we're trying to mix and match applications, those concessions have to be consciously made so you're not actually working at a detriment to your net horsepower. So the exhaust world has got a lot of technical components to it. Understanding how those components interact will hopefully let you make a better choice in selecting the best design for exhaust that you need for your car.